Hi, so today we're going to be working on another problem. This one's not an original. This is inspired by a problem in the book by Devore, and there's an original subpart to it. So let's get down to it. So consider student S who receives n internship offers that may range from unpaid internships to perhaps even a monthly stipend of many lakhs. Assume that probability density that receives a certain salary offer is constant. Determine the maximum likelihood estimator and the method of moments estimator of the highest salary offer S could ever get in the market. Cool. Okay, so already we can see that this is turning out to be a problem which is going to be based on continuous random variables, right? Because of the mention of the word probability density. Secondly, we are also given the thing that probability density is constant, and we can see that the domain of all of our random variables over here, namely the salary offers that we'll be receiving, S receives, is going to be uh, varying between 0 to some maximum, let's say, I don't know, theta. Right. So we can see since the probability density is constant, we know that f of x is constant, and that secondly, because of the normalization condition, we know that the integral of f of x across all real numbers is going to be equal to one, which basically means that we already know that our probability distribution for the salary is a uniform distribution. All right, cool. And now we would like to estimate the parameter of this uniform distribution. We'd like to know which one of these estimators is a better estimator, why is it a better estimator, and then finally, this is the original part to this problem that I made up. Is the range of the N internship offers a good estimator for the interquartile range of the internship offers S could get in the market? Namely, is the sample range a good estimator for the interquartile range of the population? So let's get down to it. All right. So firstly, obviously, some basic setup. Let x1, x2, and so on be the continuous random variables that denote the internship offers, as in the amounts in the internship offers. They can vary between 0 to theta, as I already said. And we know the distribution, it's a uniform distribution on the interval 0 to theta. And that's exactly what I've written here. This is what you see, and this is true for all I bit from 1 to n. Obviously, whenever you write that in the paper, you also have to write it beside this function, but I'm lazy. So next, we also a very very important assumption over here that you should explicitly state during your analysis is that you have to assume that budget constraints do not bind companies. Namely, ideally speaking, you might the maximum salary that you might earn, that's all right, but ultimately you have to assume that all the organizations out there are going to offer you anywhere between 0 to theta. It's not like any organization will offer you at most, let's say, alpha 1, a different organization will offer you at most alpha 2. Because then, in that case, defining your market value as the maximum of all of these market parameters is a very difficult analysis to work with. Right. So that's why the first assumption that we make over here is that these companies are all going to offer all of these companies are going to offer a salary all the way to theta, and the minimum salary they're going to offer is zero, basically an unpaid internship, right? And then the second thing we assume over here is that the internship offers are independent of each other. So basically what these two things do combined together is that they ensure that our variables are IID, namely that the sample that we have drawn over here, the sample of internship offers, that is independent and identically distributed. All right, cool, moving on. So obviously now we need to find the MLE, right? So for the MLE, we are gonna first have to write down the likelihood function. The likelihood function is the joint PMF of x1, x2, x, and when you know you with the parameter theta, right? And you would like to estimate this parameter theta, and for that you'll eventually differentiate this and set it equal to 0 and find out the required value. And that's what we're going to do. So, firstly, we see that all of these are independent, so you just multiply out the PMFs. But there's one thing that you need to note very, very carefully here, which is that you need to look at the domain. What is the domain of the joint PMF, right? Because over here, if you look at this, the domain of every xi is from 0 to theta, right? So that means that the domain of the likelihood function over here will also be such that you're ensuring that every xi, every input in this particular joint PMF is going to lie between 0 and theta. That means basically theta is to be greater than every input in there, right? Which makes sense. Otherwise, that input wouldn't be possible. And another last thing over here on notation is that over here you might have noticed that I have bolded an x here. It's because I would rather not write L of x1, x2, xn. This is common notation. It's basically just writing it in vectorial form. All right, cool. So that's exactly what we do. We note down that L of x comma theta is going to be 1 by theta raised to power n, because it's uniformly distributed and we just multiply them out. And we have the domain as 0 less than equal to xi less than equal to theta for all I equal to 1, 2, so on till n. So now what you do usually here is that you differentiate this and then you set it equal to 0. Now here's the problem. When you differentiate this, you're going to get minus n divided by theta raised to power n plus 1. And then when you try setting that equal to 0, you get theta equals to infinity, which does not make any sense. Right. So let's try to just analyze what this function behaves like. We can see that this is a decreasing function of theta, right? So basically, and we want to maximize the likelihood function, right? So that means that we want to minimize theta. Okay, cool. So then the question arises, okay, why don't I just set theta as 0? Wouldn't that just be the best thing to do? And you would be right. Yeah, that's right. But that does not solve your problem. You need to put the minimum value of theta that is acceptable according to these domain constraints. And 0 is not an acceptable value. Like, for example, you have three internship offers, say x1 equals to 5, x2 equals to 7, x3 equals to 9. All of these are in lakhs, okay? You're a very rich guy. All right, so you get these offers and you're like, okay, so my ideal market value out there obviously has to be greater than equal to 9. That's how I got an offer of 9 lakhs in the first place, right? And that's exactly what's going to happen here. So basically what you do over here then is that all of these inputs that you have, all of these things in your sample, you order them. You order them from the minimum to the maximum, and then you have to basically ensure that theta has to be greater than or equal to the maximum. That means the minimum acceptable value of theta is in fact the maximum of all the different internship offers that you get. And that's exactly what the MLE turns out to be. I've just written out the reasoning here. That means that basically L of x comma theta is going to be maximum for the minimum acceptable value of theta, which is maximum of x1, x2, and so on. And that's what I've done here. Note another thing here. I've written theta cap because this is the estimator that I've designed according to the MLE process. All right, cool. Now, again, this is, I think, fairly obvious. Plus, method of moments is really easy, so no point doing it. You can write out the formula for x bar as, theta by 2, and then you see, oh, okay, so theta is basically just 2x bar. Hence, that is a good estimator. That is the MOM estimator for theta. And you're absolutely right. Yeah, that's pretty much it. Uh, so now we need to quickly just now we come to the part of the analysis where we have to determine whether the estimator is better or the MLE estimator is better, right? And this is the tricky part, I think. So the way we do this is that the only other thing we've learned other than MLE and MOM was the so-called MVUE principle, the minimum variance unbiased estimator. So if we can somehow prove that, okay, one of these estimators has lower variance than the other and is unbiased at the same time, it's a better estimator, right? And that's what we're going to try to do. So over here, clearly, when you try to find out the expected value of this, so you operate the expectation operator on both sides, you get expected value of theta cap m is equal to 2 times expected value of x bar. We know that the expected value of the sample mean is equal to the actual mean, and the actual mean of any uniform variable is going to be theta by 2, right? Or a plus b by 2 in general, but a is 0 here. So that's why it's pretty easy to verify that yes, the MOM estimator is indeed unbiased. All right, cool. And now the question arises, how do you find out the MLE estimator and how do you check its expected value? So obviously, in order to check its bias, you're going to have to actually find out what the distribution of the estimator looks like. Because it's not like you can use linearity on the sort of, or any sort of operator. So that's what our next thing is going to be. That's what we're going to do next. So for that, we're going to find the sampling distribution of the MLE estimator. So let y be equal to, max of x1, x2, so on till xn. Cool. So I think we know the general process here. The way we do this is that we first find the CDF and then we differentiate the CDF to get the PDF of your newly defined random variable, right? And that's how you work with transformations of random variables in general. So that's what we're going to do. Basically, we're going to write the CDF. Fy of y is equal to p, the probability that the random variable is less than equal to some y. What was y? Y was the maximum of x1, x2, xn, and so on till xn, right? So that's why if we want to ensure that the maximum is less than equal to y, you need to ensure that every element in your sample has to be less than equal to small y, right? Like for example, if you want to find the probability that the maximum is less than equal to 5, and you have a sample of three elements, all three elements have to be less than equal to 5. You need to ensure that this happens simultaneously, hence the intersection operator here. And because we know that x1, x2, and xn, all of these things are independent, we can simply write this as probability of x1 less than equal to y times probability of x2 less than equal to y, and so on. And that's exactly what we've done here. And we the probability of x1 less than equal to y is just the CDF of x1 times the CDF of x2 times the CDF of xn. And then you finally write this out, and again be a little bit careful about the domain here. It is basically, that the CDF of the uniform distribution is going to be something of the form, 0 when you're outside the range, then it's going to be y by theta, and then it's going to be 1 when you're again outside the range towards the right. And that's exactly what happens. And finally, you differentiate this and you get this interesting expression, ny raised to power n minus 1 divided by theta raised to. Cool. So now that we've gotten this expression, I think it's time that we try calculating the expected value, which will just be yfy, right? So you do that on the interval from 0 to theta, and you are finally just going to get something like this. You're going to get n theta divided by n plus 1. That is not equal to theta. That means that your MLE estimator is actually biased. So that means that the bias, and over here you can see that the bias is negative. If the bias is negative, that means your MLE is actually underestimating the actual parametric value. And that's really interesting. But it's also actually quite logical because think about it. What is the actual probability that you're going to get the best offer out there? You're not. Like, there, we're assuming over here that there's a very large population and you're drawing a small sample from it, right? And then from that sample, what is the probability that it actually contains the exact maximum value? That probability is actually zero because of it being probability density. So this kind of makes sense. It makes sense that you're going to underestimate the true value. You're going to kind of shoot low. So don't feel bad if you get a bad offer. So what do we do next? Well, we go on to the next thing. We check the bias and we can see, okay, MOM is unbiased, whereas MLE is biased. So it seems like MOM is kind of winning the fight here. But we're not done yet. We also have to check the variances before we apply the MVUE principle. So variance of 2x bar is equal to 4 times variance of x bar. Variance of 2x bar is basically the variance of theta cap m, right? And you can quickly calculate this. It's really easy to calculate. All you need to know is that the variance of any uniform random variable is equal to b minus a whole square divided by 12. This is a standard result. You should honestly have this in your head by now. All right, cool. Another thing to note here is all of these are identical and independent. That's why we're able to sum them up like this, and that's why all of them just come out to be theta square by 12n, theta square by 12n, and so on. So that's why ultimately you get the variance of this as theta square by 3n. So two things to note here. Number one is that this is proportional to 1 by n, meaning that as n tends to a larger and larger number, as you go through more and more offers, you're probably gonna the variance is gonna tend to zero, meaning that you're gonna get closer and closer to the true value of the estimate, which makes sense. And secondly, is that this is proportional to theta square. That means that if your true value in the market is actually a really big value, like if you're, let's say, worth, like, I don't know, like some crazy 40 lakhs per month, then the probability of you getting a bad offer or not actually having your true potential realized early on is pretty high because of the higher variance that's there, assuming of course that you're modeling things as a uniform distribution. Again, being realistic here, that's not possible, Okay, it's probably going to be something like an exponential distribution or some kind of a gamma distribution. But let's try to simplify things and just work with the uniform distribution, right? Now let's try finding the variance of the MLE. This is a slightly harder calculation because you have to do an integral, but it's not particularly difficult either. You just have to do, y minus the actual expected value of y square times, the probability density integrated. Simple integration. You can do this yourself. And it comes out to be n theta squared divided by n plus 1 whole square times n plus 2. And this is fascinating because you can clearly see that the overall degree in the denominator, after you cancel out this n degree as n tends to infinity, is that it's proportional to 1 by n square, right? So it's you can clearly see that this will tend to 0 faster than the MOM estimator will tend to 0, meaning that in the long run we can clearly tell that the MLE estimator is just has lesser variance than the MOM estimator. Right. And this again, this kind of makes sense. The maximum offer you will get after 1,000 offers is probably going to be closer to your real true value than, let's say, the average of the 1,000 offers you've gotten so far. So that's why now the question arises, okay, we can clearly see. In fact, you can also prove that this is greater than, so this is less than theta squared by 3n, or basically that n plus 1 whole square times n plus 2 is greater than 3n for all positive n. You can even prove that actually by just working through the cubic equation and showing that that particular cubic is sort of always above the x-axis when x is greater than 0. That's an interesting calculation, but I'll leave that to you as the reader. All right, cool. So now here's the thing. You cannot apply the MVUE principle because the MLE is biased, but it has lesser variance, whereas the MOM is unbiased and it has more variance. So you kind of have to you will have to pretend to trade off biasedness for variance. And there is no clear cut way to do that. It's not like, oh, okay, you always have to prioritize bias over variance or vice versa. Right. So here is where I think I'm going to direct your attention to something that we did at the very, very beginning of class, which is something known as the mean squared error. I think the most relevant thing with respect to an estimator is the error that it's going to produce on average, right? And that's what we intend to measure. We basically, whenever you see that, okay, you cannot tell which estimator is better purely on the basis of bias and variance, you have to judge which estimator has the lower mean square error. Whichever estimator has the lower mean square error is going to be the better estimator, because it's just going to be, on average you're going to notice that its error from the true value is lesser. Like, let me tell you something over here. Just because something is on a bias does not necessarily have to be a bad thing, right? Like, for example, over here the MLE is biased, yes, but you can see that clearly. The If you overshoot the MLE, you're gonna, like, basically if the MLE overshoots the MLE is always going to undershoot the theta value, right? But at the same time, we also need to keep in mind that the MOM estimator is sometimes going to undershoot as well as overshoot, whereas the MLE will only undershoot the estimator, right? And this might be something that you actually desire, right? You might always desire that, okay, the mean squared error should be small and it should be onto it, and the error should always be negative. Maybe that's what you desire. So you really don't know yet what you should be doing. So that's why we move on to the next metric, which is the mean square error. And that's what we do. So the mean square error is defined as expected value of theta cap minus theta whole square. Theta cap is the estimator, and theta is the actual expected value of the estimator. And this is a very easy formula to prove. Nevertheless, I encourage you to actually work through the calculation yourself. How do you go from the LHS to the RHS? Okay, cool. And then basically, theta cap over here denotes the MLE estimator. So we knew that the MLE bias was minus theta by n plus 1. You square that, you get this quantity. And when you squared, there's a typo here, it appears. Basically, there is supposed to be a square symbol over here. And you add them, you get this quantity, and it's all good. All right, cool. And then on the other hand, the MSE of the you might notice again over here that the mean square error is just equal to the variance when the estimator is unbiased, whereas it's equal to the, this thing. So again, something very, very surprising happens here. And the surprising thing is that MSE of theta cap is always less than MSE of theta m cap. You can prove this. This is even easier to do. You just have to like work with a quadratic and prove that it's always greater than 0. In fact, I think the quadratic turns out to be n squared plus 3, n squared plus 2. So it's even easier that way. So yeah, basically you see over here and you see that, okay, so hence the MLE estimator is actually indeed better than the MOM estimator. And that would be the end of this problem, except for the part that I designed, which is what about sample range? So I think firstly you need to notice over here that sample range is going to be the maximum of these x1, x2, and so on, minus the minimum of x1, x2, and so on, right? And then you find out the distribution of this. You try to find out the expected value of this. You try to find out, okay, whether this expected value is equal to the interquartile range. The interquartile range note over here is just going to be theta by 2, because it's going to be from the value theta by 4 to 3 theta by 4, right? And you have to check if that expected value is equal to theta by 2. And if it's not, then what you do is you look at the variance and you check if it's at least a good estimator for the interquartile range. And let me tell you something, finding the distribution of the sample range is tricky. It's a tricky calculation, and it reminds you of those good old double integrals that we once did last semester. Loved that semester, right? Loved M1. Um, so, yeah, I'm going to leave that part to you. If I get enough demand, I'll make another video explaining that calculation. But in the meanwhile, let us just take a step back right now and analyze what we've done so far. Right. So, and let's try working on some extensions to these problems and, just see what are we gonna get. Okay. So first question, I think you guys might have clearly noticed that you can very easily construct an unbiased estimator from the MLE estimator. All you have to do is that you have to multiply n plus 1 by n times whatever theta cap. So your unbiased estimator would be n plus 1 divided by n times maximum of x1, x2, and so on till xn. And that's okay, that's fine. But my question to you is that, is this really a good thing? Because think about it, when you increase the bias, say when you reduce the bias, you are increasing the variance. If you don't believe me, you can check it out yourself. You'll basically be finding out the variance of n plus 1 divided by n times theta cap, right? Which is basically n plus 1 square divided by n square times theta cap. So yeah, you might claim that, okay, in the long run we're not really increasing bias because you're multiplying a term that is of order 0. But still the question arises, is this really the best thing we can do? And the answer to that question is not so easy, because the mean square error, which should be the primary metric whenever you're analyzing any sort of an estimator, the mean square error is going to be dependent on both the bias as well as the variance. So if you make the bias go all the way down to 0, you're increasing variance a little bit. So what if you make the bias go down a little bit and you increase the variance a little bit? Like, will that lead to the optimum minimum mean square error? What should you do here? And that's exactly what you should try to address. In fact, I encourage you to try constructing an estimator that is a minimum MSE estimator. The way you can do this is probably just say, okay, I know that the MLE is uh, the MLE is in fact a max of x1, x2, xn. So let C times max of x2, x1, xn be the minimum MSE estimator, and and then you try to find out the mean square error of this, and then you differentiate that expression with respect to C, set it equal to 0, verify that whatever value of C you're getting leads to a minimum, and then check it out. And actually, in this scenario, it's a very interesting result. I'll leave you to derive it yourself. It actually comes out to be n plus 2 divided by n plus 1, which is just fascinating. And lastly, when we see, okay, how do you also come up with a minimum variance estimator? So again, you do the same thing. You multiply a scalar constant with this estimator that you've already obtained, and then you try to find out the value of that scalar constant in terms of, let's say, known constants like the population size or the sample size, and you figure things out. And that's pretty much it. Except there's one more thing to think about. When you do this problem, this is purely, by the way, just working at hypotheticals. I'm going to ask you something. Is it possible that you can construct an estimator in this particular situation when we are okay with a certain amount of error, but more estimation error is bad? Like, what I mean by this is, like, for example, again, in this scenario, you have internship offers, and let's say you don't want to overestimate your internship offer or underestimate your internship offer by more than, let's say, 5%, right? So you're like, okay, how do I construct an estimator that has a really, really, really catastrophically low probability of actually making this error? And for that, what you're going to do is that, again, you take the MLE estimator, which is our favorite estimator, right, guys? And you multiply a constant C with it, and then you say, okay, so C times my MLE estimator should be such that P of your, let's say, new theta cap C theta cap minus your true value theta, the modulus of that is less than E epsilon. And then you find out that probability exactly. And then you differentiate that probability with respect to C, set it equal to zero, try to find a concrete value of C, and so on. Right. And I did that. Actually, I did that because I'm pretty jobless. And it turns out that C value turns out to be dependent on theta. And a point estimator cannot be dependent on the parameter it's trying to estimate. Because, that means that you would know the parameter you're trying to estimate, which defeats the purpose of the estimation. Right. So, in fact, I think I encourage you to try finding a better solution than I did. Try to find out a C value that actually, in general, on average, across all theta values, serves as a pretty good estimator for this sort of catastrophic estimator. Right. And I think on that note, I'm going to sign off. That's enough yapping. You guys, if you want to do the problem after this, and if you're curious for more after even that problem, you guys can look up these things called order statistics, right? Because I've always tried to construct an unbiased estimator for the median, or maybe some sort of metric which tells you, okay, how can you determine whether a distribution is symmetric, right? Maybe you want to determine with 80% certainty that, okay, this distribution is probably symmetric. So for that, again, you need an estimator which for the mean and an estimator for the median. And you need to show within some probability that they're going to be equal to each other. And if they are equal to each other, maybe you can do a hypothesis test, or maybe you can construct some sort of confidence interval to show that, okay, yeah, the mean will always be this close to the median, and then deduce that, yes, the underlying distribution has to be symmetric. And all of these are really interesting ideas, but they're out of syllabus. So if you want to think about them, think on your own time. On that note, I sign off. Bye bye.